guys, in this video we are going to talk about exceptions and drawing Lewis dot structures when there are exceptions involved and resonance. Let's get started. All right, so obviously we already talked about last class that hydrogen isn't accepted, but in addition to hydrogen being an exception, oops, got a little intruder here, Lucy. Okay. Sorry, guys. So, hi, everyone. In this video, we are going to talk about exceptions and resonance. So let's get started. Okay, so last class we already talked about hydrogen and that hydrogen only needs 2 electrons. But this time, I want to mention boron and beryllium. All right, so boron only needs 6 electrons typically to be full. And beryllium needs 4 electrons to be full. Okay, so they don't have to satisfy the octet rule because they're satisfied with 6 and with 4. So let's go ahead and draw this Lewis structure. So this one we have boron. We have 1 boron, and boron has 3 valence electrons. Plus we have fluorine, and we have 3 fluorines. And each fluorine has 7 valence electrons. So 21 plus 3 gives us a total of 24 valence electrons that we can use here. All right, so boron is going to be our central atom because it's less electronegative than fluorine. I'm going to come draw it over here where I have a little more space. So I'm going to put my boron in the center, bond 3 fluorines to it. So at this point, I have used 6 electrons. I have 24 total, so that means I still have 18. So I'm going to start filling the octets of my outside elements. So I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I've used a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used all of my electrons that I needed to use. And let's check that everybody is full. So this fluorine will come over here. 2, 4, 6, 8. That fluorine's good. 2, 4, 6, 8. That one's good. 2, 4, 6, 8. So all my fluorines have that octet rule satisfied. Then my boron has 2, 4, 6. And boron only needs 6 electrons, so that boron is full, and so this Lewis structure is good to go. All right. Now, guys, with our exceptions, there are some that are never going to follow these. So there's a lot of elements that can be an exception, but there are some that will never be an exception. So carbon, nitrogen, oxygen, and fluorine should always have 8 valence electrons, no matter what. You should never have more, never have less. Okay, so those always are going to follow the octet rule: carbon, nitrogen, oxygen, fluorine. But some elements in period 3 and beyond are going to exceed the octet rule. So below period 3, the third row of your periodic table and beyond can have more than 8 valence electrons. So like, for example, SF6, the sulfur has 12 electrons around it. And basically what's going on is those extra electrons are paired with electrons that are in the d orbital. And so the first and second rows can't, those in the first and second energy level can't do that because they don't have those d orbital electrons for those bonds to happen. And if the octet rule is going to be exceeded, it's always going to happen on the central atom. So that's something I always write down, is everything weird happens on the central atom. So it's not going to happen in your outer atoms. It's always going to happen to your central atom. I am writing that terribly, so I'm going to rewrite it so that you can actually read it. I don't know what's wrong with my handwriting today. Yes, thank you for your feedback, Lucy. All right, let me zoom in and maybe my handwriting will be better. Everything weird happens on the central atom. Okay, let's do some practice here, guys. So we're going to start with I, 3, -1. Okay, so we have 3 iodines, and each iodine has 7 valence electrons, plus we have that -1, so that tells us to add 1 extra electron. So I have 21 plus 1, which gives me 22 valence electrons to work with. All right, our only element is I, so I is definitely going to be our central atom. All right, and I'm going to go ahead and bond the other 2 I's to it. So far I've used 4 valence electrons. I still have 18 more to go, so let's start filling our octets. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so at this point we have used 16 electrons, but we have 22 to use in total. So I'm going to go ahead and fill up my central octet. So I've got, then I've got 18, 20. I still have 2 more electrons, so I'm going to stick them on my central atom like this. And now my central atom has, let's count them up, 2, 4, 6, 8, 10 electrons around it. It is in the 3rd period or below, so it can hold those, while each of my other iodines both have 8 valence electrons around them. So everybody is following the rules here, and so this Lewis structure is good. Okay, let's do the next one. So we have chlorine trifluoride. All right, so we have 1 oops, highlighter. Okay, so let's try that again. We have a 1 chlorine, and each chlorine has 7 valence electrons. Plus, we have 3 fluorines, and each fluorine has 7 valence electrons. So I have 7 plus 21. That gives me a total of 28 valence electrons here. Okay, chlorine is going to be my central atom, and I'm going to go ahead and bond 3 fluorines around it. Okay, so at this point, I have used 6 electrons, and I still have 28. So let's go ahead and fill out our outer atoms octets. Try saying that 3 times fast. It's not easy. All right, so we've used 6. So 2, 4, 6. That fluorine is full. 2, 4, 6. That one's full. 2, 4, 6. Okay, those are all full, and so far we have used, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used 24. Our central atom still isn't full, so I'm going to add 1 there. So now we've used 26. We still have 2 more valence electrons, so once again, we're going to pop them on our central atom, and chlorine has now 10 valence electrons around it, but each fluorine is full with 8. So that Lewis structure is good to go. All right, I want you guys to try out this one on yourself, by yourself. So pause the video now and then come back whenever, I don't even know what I'm saying, but pause the video and then come back and watch it. And okay, try this one on your own and pause the video, try it on your own, and then start the video again when you're ready to go over the answer. Words are hard, guys. Words are hard. Okay, so this one, our central atom should have 3 lone pairs and 2 bonds around it, and then each chlorine is bonded to it with 6 lone pairs of electrons. All right, let's talk about resonance now. So, basically resonance occurs when there is more than one valid Lewis structure for a molecule. And basically what is going on, it typically happens when we have a double or triple bond on one element that really could be on another one. And so what actually happens is that our structure ends up being kind of an average of all of the structures that we draw. And this concept is needed to fit the localized electron model. But remember, electrons are actually really delocalized. Okay, so let's go ahead and draw some resonance structures. So our first one that we have is benzene. And guys, benzene is a carbon ring. So it's going to form a ring-like carbon shape. So we have 6 carbons here. And each carbon has 4 valence electrons. And we have 6 carbons. plus one hydrogen, or I'm sorry, one valence electron in each hydrogen, and we have 6 hydrogens. So 4 times 6 gives us 24, plus 6 tells me that I have a total of 30 valence electrons to work with. Okay, so first things first, it's going to form a carbon ring. So what that looks like is I'm going to basically have a hexagon of carbons bonded together. My hexagon is looking really good. Oh my word, it's pretty bad, but there you go. There's my benzene, my carbon ring. Okay, so at this point we've used 2, 4, 6, 8, 10, 12 electrons. We still need to bond our hydrogen, so we're going to bond 1 hydrogen to each carbon. All right, so now that we've done that, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. All right, but you guys may notice that our carbons all only have 6 electrons. So I can go ahead and kind of try to fill up some of my carbons. So I've got 6 electrons to use. There's 2. All right, there's 2, and there's 2. Okay, that didn't get very far. So what we're going to have to do is we're going to have to use double bonds. Okay, so if I put a double bond between those carbons, all right, now we've used 2 valence electrons there, and both of those carbons have 8 valence electrons, so they're good to go. All right, since this one already has 8, we don't need to put a double, like this one right here already has 8. We don't need to put a double bond in between it and the other one, but we can put a double bond right here. All right, same thing. Now both of those have 8 valence electrons. And again, we're going to put a double bond right there as well. Okay, so now this structure, we've used all of the electrons we needed. We've used all 30 of the electrons, and everybody has that full octet. But what's to say that my structure couldn't look like this instead? Let me draw it really quickly. All right, and with my double bond here, here, and here. And guys, in truth, it could. So my structure could be drawn either way. And so this is what we call resonance. And basically when we have resonance, it's when we have a double bond that could be moved and could be on a different atom. So in this case, it could just be flapped over one space and on all the different carbons that it was on versus in the original one. And this is called resonance. And what actually happens in a resonance structure is that really those double bonds are kind of moving. And so that electron may be between, that double bond may be between these 2 carbons for a while, and then it'll move on and be between these 2 carbons. And so instead of really having double bonds, what ends up happening is we have these kind of hybrid bonds. They're kind of somewhere in between, but they all end up being the same length. Because those pairs are moving. And so there's no like true double bonds, but rather kind of like floating double bonds, I guess is the way to put it. So yeah. So that's really important to say is that all bond lengths and angles are the same in these resonance structures. All right, let's do the next one. So we have SO3. So we have 1 sulfur. Oh my goodness, forever using the highlighter. Okay, so we have 1 sulfur, and each sulfur has 6 valence electrons. Plus we have 3 oxygens, and each oxygen has, nope, not 7. Also 6 valence electrons. So we have 6 plus 18, which gives us 24 valence electrons to use here. All right, sulfur goes in the center, and I'm going to go ahead and bond my 3 oxygens to it. All right, so I've used 6 electrons. I have 24 total to use, so I'm going to go ahead and start filling up my octets here. So I have 18 more. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so I've used all of my electrons that I have, so that means I need to steal a pair from my oxygen and make a double bond. But guys, couldn't that also have gone on this oxygen? Sorry, my bond looked bad. Oh my goodness, it looked worse. Or even the other oxygen. So that is resonance, where basically our bond could go on any of the oxygens or any of the other things. And so we have to draw all of the structures. And really it ends up being a sum of all three of them. So that bond is sometimes on one oxygen, sometimes on the other. So they all kind of have hybrid somewhere between single and double bonds. Okay, well, hopefully that helps and that you feel confident with resonance and exceptions to Lewis rules. Bye.